I'm Anil Kumar. Welcome to my series on calculus. We'll now discuss gradient of a curve and we'll find the gradient using first principle. So in this particular video, first thing is to understand the very basic concept, and then I'm going to take up a couple of examples here. These examples will be on different kinds of functions. So we'll take up linear function and we'll find gradient at a given point. Then on a quadratic function, we'll derive a general expression where gradient will be found at x equals to a. Then in a cubic function, we'll actually find a general expression and then see how to find gradient at different points, right? X equals to -1, 0, and 2. Then in the last two questions, we'll take up the function, which is the parent square root function, and we'll show that the gradient is non-negative. And for a reciprocal function, we'll show that it is always negative. So that is interesting group of questions which I have selected. As far as some high-level questions are concerned, we have got hundreds of them in the playlist. I'll provide you a link for those, right? So let's first understand the very basic concept. So I'll just sketch a general curve here to explain the idea of gradients. So let me sketch a function which has all kinds of gradients. Let's say we have a function here which is kind of like this, and then from here it's almost vertical like this, right? In the next part, we'll take a function which continues. We are talking about continuous functions, right, like this, and then say it goes like this. Okay. So I've just sketched a function here. Okay. Now, in this function, if I draw slope at a given point, that gives you the gradient, right? So the gradient basically is, let's draw some slopes. So if I draw a tangent at this point, right on the top here, where it is a turning point, then the tangent will be a straight line. So in this case, there is no rise, right? The straight line is a horizontal line. And if I draw a tangent somewhere here, for example, right? So it will be a line like this, correct? So in this case, it is rising. So we say gradient is positive. On the other hand, if I draw a line which is somewhere here, for example, like this, okay, in that case, we notice that the gradient is negative. The line is kind of going downwards. Okay. So basically, what we see here is that the term gradient, really we are talking about slope of tangent line. Right. So at this point A, we say slope is 0 at A. So we say gradient at A is 0. So this is a horizontal line. Now here the gradient is 0. Very important, right? So all the turning points will have a gradient of 0 on the curve. Now we have a point on the right side of this. Let me call this as let's say point B. Now at point B, we have a negative gradient. It is going downwards, right? On the other hand, at point C, we have a positive gradient. Do you see that? Now at times, we could have gradients which are undefined. For example, here, the steepness, do you see, as you move from here, the slope is increasing, correct? At this point in the origin, it is almost vertical. So the tangent is vertical. So we have a vertical tangent. So here we say gradient is undefined. So we have used the word gradient to indicate a slope of a tangent line at a particular point, right? Now, you know what slope is. Slope basically is ratio of rise over run, correct? So at any point, what you could do is you could make a triangle. So if you make a triangle, rise over run will give you the value of gradient, right? So that is what we are talking about. Okay. With the help of these examples, we'll explore further. However, you understand from here that at turning points, the gradient is 0, the tangent line is horizontal. If the tangent is vertical, then the gradient is undefined. If the graph is rising or increasing, then at any point during the interval where the graph is increasing, it will show a positive gradient. So positive gradient also increasing graph. Similarly, a negative gradient will mean decreasing graph. A horizontal line means a turning point. Let's use a different pen here. A horizontal line means a turning point. So these terms could also be used in your word problems related to gradients, slope, tangents, and things like this. Correct? Now, we'll take up these examples and try to understand what is first principle, right? So we have talked about the first part, which is gradient of a curve. We got a broad overview of this. Now all we are going to look into is what is first principle with the help of these examples. Okay? So let's begin with the linear function. I've taken this linear function as 1 minus 2x, and we'll figure out what is the gradient at the point 2 minus 3. Now, straight lines. Straight lines are unique in a way that we have a constant gradient. Constant gradient means the slope is constant. It never changes, right? So if I have to sketch this line 1 minus 2x, is basically means that I have a point 1, which is the y-intercept. Slope is minus 2. So if I move 1 unit on this side, I have to go down 2 units, correct? So I get the next point. 1 unit this side, 2 units down, I get the third point. So what I get here is a line which is kind of like this, right? Where the points are, so this point here on the line will basically be 1 minus 1. That means I moved 2 points. And this next point which I've shown here will be 2 and 2 more down, right? Since it is 2 down, right? So 2 more down will be minus 3. So if I sketch a line based on this particular equation, that is what I'm going to get. Perfect. So what I did was that I just drew a table here. For different values of x, I found the value of f of x. Starting with x equals to 0, I got 1. At x equals to 1, if I substitute here, I get minus 1. And if I substitute x as equals to 2, I get 1 minus 4, which is minus 3. Using these points, I have plotted a line. You got the idea, right? So if you see, I have a set of points which are 0, 1, and then I have 1 minus 1, and then I have 2 minus 3. Now what is gradient? Gradient basically is slope, which you know is rise over run. Now for a line, we can always find y2 minus y1 divided by x2 minus x1 to get the slope. Now in this particular example, as you can clearly see, these are my three different points. Let me call them A, B, and C, right? So these are my points now, A, B, and C. So if I have to find slope between A and B, what will it be? Difference in y values, which is -1 over difference in x values, 1 minus 0. And clearly this is -2. Similarly, what is the slope between B and C? Well, this slope between B and C is difference in y values, which is -3 minus of -1 divided by 2 minus 1. Now that is again -2. So if we have a straight line, you will see that the gradient is always constant. You can take any point, right? So the gradient is 2 at any point on this line. Is that clear to you? Perfect. So that is what a slope is going to be. In most of the functions, what you will notice is that this constant does not make a difference. If I change this constant to a new value, for example, if I write f2x, it's a different function, right? In this case, let me write this as 2 minus 2x. In that case, I will get a line which will be parallel to this, correct? But all the points on this line will also have a slope m same as -2. So the value here, the constant value, makes no difference as far as the gradient is concerned. So what you notice here is that a translation makes no difference. Perfect. So that is also a very important observation as we move along. It is going to help us a lot. So I hope you're getting the concept. So we have very simple examples, but a lot of concepts built in them. So now let's move on to quadratic functions. Okay. So now we'll consider quadratic function. I have taken g of x as x squared minus 3, and we'll try to figure out what is the gradient at a point x equals to a. So let me sketch this function here. Drawings help, right? So the function -3 means x squared moved 3 units down, right? So we'll just draw a graph here which has moved 3 units down. So this point is the turning point at -3. So at x equals to 0, I get -3. Perfect. Now, if you consider this particular graph, then any point in general can be written as what? If I say x equals to a, then the y value is g of a, correct? Since the function is g of x. So I have a function here which is g of x is equal to x squared minus 3, right? So what is g of a equals to? Well, g of a will be a squared minus 3. Correct? That is how it is going to be. Now, you will notice that if I draw a tangent at any point here, for example, it is negative, right? It is less negative, 0, positive, and pretty steep, right? So what we see here is that the gradient is changing. So whenever we talk about curves, we move from left to right whenever we're discussing curves. So what I want to say here is that the gradient is changing, and you will see all over the curve, it is going from high negative to low negative to 0 to positive to high positive. Correct? So it is a very large negative value, less negative value, 0 here at the turning point. Right? So we have a turning point here where it is 0, then it starts becoming positive. Correct? So the slope is going in this order, which we can say is always increasing. You see that? So if I have to really sketch a slope here, so let's say we call this function, which is, let me write this as g of x. Now if I want to write the gradient as g dash of x, calculating from different values, I'm going to get a graph which will be kind of like this. Do you see that? So on the left side of the 0, we have a negative value. At 0 where we have the turning point, it is 0, and the gradient becomes positive and positive as we move to the right. That's a very important criteria. Okay. Now let us see how to find this gradient using the first principle, and what after all is this first principle. Well, in case of the line, we just took any 2 points and it worked for us since the gradient was constant. But here the gradient is not constant. So let me take a small portion of this. So what I will do here is I will take this small portion and enlarge it, right? So let me enlarge this small portion, right? So what I'm trying to do here is enlarge this portion, right? So now again I have the same thing, which is my point A here, right? So on this graph here, I have x equals to a. Now to find gradient, what I really do is that I take up another point which is very close to a. Let's say very, very close, but on a scale which has been enlarged, I will consider that to be here, right? So let's say this is my point which is very close to a, and I'm saying this is at a plus h, where h is approaching 0. That means it is very close to a. Is that clear to you, right? So in that case, the value here is g of a, and the value there will be g of a plus h, right? So if I now draw a tangent, a secant I should say, joining these 2 points, right? So if I join these 2 points, it is definitely not a tangent, but it gives me an idea of the slope, right? So the slope will now be difference in these two values, which is delta y over delta x, these two values. Is that okay? So now what I understand from here is, what is g of a plus h equals to? G of a plus h, substituting for x a plus h, we get a plus h whole square minus 3. And that gives you a square plus 2ah plus h square minus 3. So this is g of a plus h. Clear? Now from here, we can actually find the slope, right? So we'll write this as a slope. So slope, which is the gradient for us, will be change in this, right? So which will be g of a plus h minus g of a, which is delta y, right? Okay, let's write like this. We'll write like this. We'll write this as equal to delta y over delta x. Is that clear? Right, okay. Now, delta y is actually g of a plus h minus g of a, and delta x is basically a plus h minus a. So that gives you, from these values, that gives you a value a square plus 2ah plus h square minus 3 minus a square minus 3, right? So this is g of a plus h, and then we have a square minus 3. And the denominator a plus h minus a gives us the value h. So if you simplify this, what do you get? Well, the terms a square and a square cancel away, right? So this a square and a square cancel. this minus 3 also cancels. We are left with 2ah plus h squared divided by h, which I can take h common, so I get 2a plus h divided by h, which is 2a plus h. Is that clear to you? So we say that the slope, now we are talking about a secant at present, right? Since we are talking about two distinct points which are at a distance of h. Now see what happens when I take h approaching 0. Now this slope becomes a tangent slope when I employ a condition on this, that which we say limit h approaches 0. As soon as I say this, h is approaching 0, see what happens? 2a plus h. So in that case, when I say limit h approaching 0 for 2a plus h, now since h is approaching 0, we are left with the term twice a. Do you get the idea? So what we get here is that this is the slope of the tangent line, and that will be called as our gradient. Is that clear? So on this curve, we have a general expression to provide gradient of the curve. Now onwards, we are going to write the gradient as g dash a, right? G of x is a function, g dash a will be our gradient, right? And we may also use a term which is called derivative with respect to x, right? So which we'll introduce soon. So at present I can say that the gradient is, which is g dash x, is 2 times x, 2 times a for x equals to a. Just derived. For any value x equals to a, it is 2 times a. Is that clear to you? So that is how we could get an expression, and we'll call this as our general expression. And the method which I have discussed here is called the first principle. So all this method which I am discussing here is the method of first principle. Right? So we definitely have 2 points here which are slightly away, h distance away. And the idea is, as h approaches 0, slope of the secant approaches slope of the tangent, and that is what the gradient is at a given point. Perfect? On the curve. So we get our value. While we do all this calculation, we see that h actually cancels out, and what remains will be substituted to 0 to find our general expression. Correct? Let's take one more example, and this time with cubic function, and then you will surely understand the whole process. So here is a cubic function, p of x equals to x cubed. We need to find the gradient. So the question was basically to find gradient at given points. In this case, we are given x values. You need to evaluate the y values also. Now, to begin with, let us make a sketch. And this time, I'll make, we are only worried about minus 1, 0, 2 values. So what I'll do is, I'll make a very flat kind of a structure here for the curve. Okay. So that is my function, which is x cubed. So if I have these values, I could actually plot them, and I say, well, if x is values like minus 1, 0, and 2, then x cubed, which is my function, will be minus 1, 0, and 8, correct? Those are my values for x cubed. Okay. Now, we need to find the gradient at all these points. So there are now more than one point. So in this case, what we do here is that we follow the general principle, first principle, and get a general expression for x equals to a, as we did last time. You get the idea. Correct? So that's the whole idea. So we'll apply the first principle to find. So let me summarize the first principle now. We are saying gradient is basically equals to the limit h approaches 0 for the change of value of the function f of x plus h minus f of x over h, correct? So that is first principle. Now in our case, we have a function defined as p of x. I could have written p here. Let me make it p, okay. Right. So for us now the function is x cubed, right? So we'll just go with x cubed and later substitute these values after we get a general expression. So I'm taking any point here. Any point here will be x and the y point will be x cubed, correct? So that becomes a general point, right? You can say, well, I have a point here which is a, then the y value will be a cubed. You could say that, correct? Right? Okay. So that is how we could select points. So what I will do here is I will select 2 points. So we'll say our value p of a is what? P of a will be a cubed. So what is p of a plus h? Well, I'll substitute instead of a plus h. So I got a plus h whole cube. The expansion for this is a cube plus 3 a square h plus 3 ah square plus h cube. Now the gradient is what? Which is also treated as slope of tangent, right? So slope of tangent is the limit that h approaches 0 for p of a plus h, which is all this, a cube plus 3a square h plus 3ah square plus h cube minus a cube divided by h. So that gives you limit h approaches 0. Now you will see that a cube cancel away, right? So you get these 3 terms here. In these 3 terms, h is common, so I am writing h common, and I am left with 3a square plus 3ah plus h square divided by h. So now I could cancel these 2, right? So what do I get? I get limit h approaches 0 for 3a square plus 3ah plus h square, all this. Now when h is approaching 0, that means the other point is somewhere here, very close. So we have a point here which is AA. So the point here will now be a plus h times p of a plus h, correct? So that is this point. Now the difference between these two, the value here is h. We are saying h is approaching 0, right? So that gives you the tangent at the given point. You get the idea. Perfect. That is what it is. Now when h approaches 0, both these terms approach 0. So what do we get? We basically get this as 3a square, correct? So we have a general formula here. Let me rewrite. So now we can say that the gradient of p of x equals to x cubed is, we are writing this as p dash x is equal to 3a square of a, right? So we get a general expression for the gradient, and now what we could do, we could find all the 3 values, right? So we can say, well, for x values, what is the gradient? So when I substitute x as minus 1, I have expression which this is 3a square, right? So x is equal to a, right? These are my values, x equals to a. Minus 1, if I substitute, I get 3 times minus 1 square, which is 3. When I substitute 0, I get 3 times 0 square, which is 0. And when I substitute 2, I get 3 times 2 square. 2 square is 4, 4 times 3 is 12. So we get a gradient of 12. Do you see that? So with that, we find the gradient at different points. So you appreciate the utility of solving the type of question I've taken, where you're finding gradient at 3 different points. It is good and it is useful to find a general expression and then substitute the values later. Perfect? So I hope that helps. Now, at 0, you do notice that the tangent is 0. That means x-axis is actually tangent to our curve at origin. Perfect? Right. So at the x-intercept, you can say here, you notice that at the x-intercept, tangent is horizontal. So these are different ways in which we can actually write our expression and understand them, since in questions we could be asking you in those ways, right? I hope that makes sense. Okay, let's take up the other interesting examples now. Now we are going to look into square root function. Let me sketch one here and then we'll discuss that. Since square root function is always positive, it is in quadrant 1. So that's the kind of function which we have. This is square root of x, which we are talking about. Now, if I draw tangents at different points, well, I get something like this. Correct? So what you notice here is that the gradient is always non-negative. So it is always rising. Do you see that? While it is rising slower, it is steeper here. We do notice that at this place, it could be very steep, right? So, and then it becomes decreasingly steep, right? So the gradient is always non-negative. It is positive, right? And as we move from left to right, it is kind of decreasing, right? So the gradient is positive, non-negative, and it's kind of decreasing. That is what we see when we sketch the graph. Now the idea here is to prove it algebraically. That's the whole idea, right? So we are going to use the first principle to prove that the gradient is non-negative for a square root function. So let's say that the function f of x is given to us as square root of x. Then what is the value of x plus h? H should be square root of x plus h. Correct? So what is gradient? Gradient or slope of the tangent, right? Slope of tangent. Now, why am I using these different terms? In North America, we don't normally use gradient, right? So there we use slope of tangent or derivatives, right? So that's the whole idea. Okay. Now, what we learned here is that the gradient here is f of x plus h minus f of x over h when the limit h is approaching 0, where that point h is very, very small, right? So we're considering 2 points on this graph. Let's say this is 1, the other one is here, right? We are calling this point as some value x, and this is x plus h, right? And we are saying that the difference is h, which is approaching 0. That means they are very close. Since they are very close, since this is true, secant approaches tangent. And so we have the gradient at a point. You get the idea, right? So that's the whole concept. So this point here, which we're talking about, is f of x. The other point here is f of x plus h. So that difference is change in y, and this difference is change in x. So that is change in y over change in x. Do you see that part? Perfect. Now, in our case, what do we get? We get limit h approaches 0. As far as the function is concerned, f of x plus h is x plus h square root minus square root of x over h. Now, how do we solve such an equation? Well, the critical step here is rationalization. Correct? So we are going to do rationalization and then solve. So what we get here is limit h approaches 0. We have square root of x plus h minus square root of x over h. We'll multiply and divide by its conjugate, which is square root of x plus h plus square root of x over square root of x plus h plus square root of x. Now in the numerator, you're going to get difference of squares. So you get x plus h minus x in the numerator. The denominator is product of these. So h times square root of x plus h plus square root of x, right? And that basically gives you limit h approaches 0. The numerator, we are left with h, correct? And the denominator, we have h times square root of x plus h plus square root of x, right? So that's general algebra. So at this stage, these cancels. What are you left with? Well, we are saying limit h approaches 0. This approaches 0. So if h is approaching 0, in that case, I'm left with 1 over 2 square root x. Do you see that? H approaching 0, right? So we are left with 1 over 2 square root x. So that becomes the gradient. Perfect. So we can now say that the gradient of f of x equals to square root of x is f dash x equals to 1 over 2 square root of x. Now this is always positive. Square root is always positive, right? So we know from here this is always greater than 0. Do you see that? It is always greater than 0. Perfect. So we say, well, gradient is non-negative. Therefore, non-negative. Is that clear to you, right? Very important. Now here, there is a very important thing to understand, and that is, at x equals to 0, what is the gradient? What is f dash x? It is undefined. So that means here, we have a vertical tangent. Do you see that? At x equals to 0, it is undefined because denominator becomes 0. So for a square root function, it is extremely high to begin with, and then it tapers down, lowers and lowers, right? But it is non-negative. Is that clear to you? So in these sort of videos, we have learned a lot of concepts about gradients and different functions. So I hope you find it interesting and useful. We'll take a small break now and then take up the last example to wind up. I hope you enjoyed the break. It is always good to be with nature for some time, recharge, come back and start. So now we are going to look into reciprocal functions. The question here relates to that the gradient is always negative for a reciprocal function. Now we're talking about parent reciprocal function, which is 1 over x. Right? So what I mean here is the function is 1 over x. The graph of such a function is, as you know, kind of like this. Correct? So it is approaching 0 when x is very large, and when you are approaching 0, it approaches negative or positive infinity, as you can see from the particular graph. Clear? So for us, the function f of x is basically equal to 1 over x. Now, if I take any point on this function, for example, let's take a point here, which is a. Let's say this point is a, then the value of the function will be f of a. And if I take another point which is slightly away, we say a plus h, in that case, this value will be f of a plus h, correct? So at f of a, the value is 1 over a, and for f of a plus h, it is 1 over a plus h. Clear? Now, if you take any 2 points, you will see that the gradient is basically negative, right? So at any point, gradient is negative, right? Do you see that? So we observe that the gradient changes from minus infinity, right, to 0, but negative, right? So it is coming downwards. Minus infinity means almost, this is called the vertical asymptote. X equals to 0 is vertical asymptote, right? So when you are approaching 0, the gradient is undefined, correct? So as x approaches 0, gradient is undefined. Clear? So these are a few things which are important about the reciprocal function 1 over x. Now, how do we show this mathematically? That's what we are going to look into. So now we say that the gradient, which we are also calling as slope of tangent, and we'll soon call it as a derivative, is what? We'll denote it by f dash x is the limit h approaching 0. We have taken 2 points, f a plus h minus f of a, right, over h. So this is as good as saying delta y over delta x, right, where delta x is approaching 0. So that is what is first principle, right? So we're kind of reviewing all the concepts which you have learned so far. Now, we can substitute these values and evaluate. So that's so simple, right? So it is limit h approaches 0. A plus h is 1 over a plus h, that is f of a plus h, minus 1 over a, which is f of a over h, correct? Now, this thing could be written as limit h approaching 0. We can take this as a common denominator, right? So we get a times a plus h as common denominator, cross multiplies, we get a minus, within brackets, a plus h, and everything over h, correct? Now rewriting the same thing, I will write this f dash x, the gradient function, is limit h approaching 0. Now in the numerator, when you open this, what do you get? A minus a is 0, we get minus h in the numerator, right? When you open this up, we can take this in the denominator, we get a times h times a plus h. Clear? Now here, h and h cancel, right? So as soon as you cancel them, you get this as equals to limit h approaching 0 minus 1 over a times a plus h. Now if h is approaching 0, we know this term is also approaching 0. So we could now write this expression as minus 1 over a squared. Do you see that? So it is negative. A squared is always positive, and so we get this function is always less than 0. Is that clear? So that is how we show that the gradient is always negative for a reciprocal function. Is that clear to you, right? So that's how we kind of show it. And we do have a general expression here for 1 over x as minus 1 over a squared, right? So I hope you enjoyed this set of videos, set of examples in the video, where we have taken all types of functions And we could actually twist these things in a very different way. And we can say find point or points on f of x equals to 1 over x, where gradient is, since it is negative, we have to take a negative value, negative 5, right? So let this be a question for you. So that could be a very interesting test question for you, right? So we do have an expression for it, and then you can find a point very easily, right? So I hope that helps. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.